All right, now let's talk about Gauss-Markov assumptions. Those 5 assumptions that we're going to need in simple regression analysis. And just as a quick reminder, why do we need it? We need them because at the end of the day, we want to say something about the expected value of our estimator, which is beta hat, the variance of our estimator, and the distribution of our estimator. So that's why we need to make assumptions. Without those assumptions, I cannot be sure that my interpretation is a causal interpretation. So now let's quickly review these 5 assumptions that we need. We're going to review these 5 assumptions in chapter 2 and 3. In chapter 4, we're going to relax one of them and then maybe talk about a relaxed version of these ones. But let's focus on the simplest version of these assumptions. So assumption number 1, it's linearity in parameters. So the model should be linear in parameter. So let's read through the assumptions. It says that in the population model, the dependent variable y is related to the independent variable x and the error or disturbance terms u. And this is a relationship, right? Where beta 0 and beta 1 are population intercept and a slope parameter. So the key term is that the entire model is linear in parameters. So what does that mean? So let me give you an example. This model is completely linear in parameter, right? So y is equal beta 0 plus beta 1 x plus u. We do need linearity in parameters. So I have to look at the parameters and see if the model is linear in parameters or not. What does it mean? It means, do I see beta 1 squared, or a square root of beta 1, or beta 0 cube, or 1 over beta 0? Do I see something like this? If that's the case, that's a violation of this assumption. Otherwise, there's no violation. So we focus on the term linear in parameters. So what does that mean? It means that this model is perfectly fine. If I write beta 0 plus beta 1 x squared plus u, this is perfectly fine. Yes, the model is nonlinear in x, but it is linear in beta, and that's all we need. So let me give you another example. Y is equal beta 0 plus beta 1 square root of x plus u. Again, fine, fine, fine. One last one. Log y, this is logarithmic version of y, is equal to beta 0 plus beta 1 log x plus u. Perfectly fine. There's nothing wrong with these models. They're all linear in parameter. What is the example of a model which is nonlinear in parameter? Okay, look at this one. Y is equal beta 0 plus 1 over beta 1 x plus u. This model is nonlinear in parameter, so it's a violation of assumption number 1. Why do we need this assumption? Because without this assumption, the OLS cannot solve for beta hat 0 and beta hat 1. So the mathematical explanation is a little more challenging, but I'll leave it to you guys, if you're interested. And if you had any questions, I'm going to go over it in our face-to-face class. But for now, just remember, we need linearity in parameters, not the variables. Okay, assumption number 2. Assumption number 2 is kind of obvious. It's random sampling. And we talked about this random sampling assumption. Without the random sampling, our estimators are going to be biased, right? So we talked about different sampling biases, and we said, okay, the solution to avoid all those biases is to have a random sampling. So this is assumption number 2. So we assume that we have a random sample size of n, so this is your sample size. And following the population model in equation, well, again, this is equation number 2.47. All right, so the first 2 assumptions are clear. Number 1, linearity in parameters. Number 2, random sampling. Okay, now let's say, again, what is the goal of making these assumptions? Remember, at the end of the day, I want to say something about the expected value of my estimator and my estimates. These are the estimates, right? And the variance of the estimates. And eventually the distribution, the PDF of all those estimates, right? So let's talk about the expected value and variance of the OLS estimators, and then in order to say something about them, we're going to make a couple of more assumptions. So the estimated regression coefficients or random variables, we already talked about them. We said that the beta hats themselves are random variables. We can have thousands of them based on thousands of different sampling, right? Because they're calculated from a random sample. So this beta hat 1, this is, we have seen this before. This is the equation for beta hat 1, and this is the equation for beta hat 0. And from each sample, we get one of them. So if I keep resampling from the entire population, I receive multiple of these things. So at the end of the day, we are interested to see what are these numbers. What is expected value of beta hat 0? What is expected value of beta hat 1? And what is the variance for either of them? Okay. So the question is what the estimators will estimate on average and how large the variability is in repeated samples. Okay. So this is the subtle part. In real world, in this course, in econometric, in the Wooldridge dataset that we're using, we only deal with one sample. I cannot emphasize it more. We only deal with one sample. However, we are really interested to be able to say something about the average of these things. What if, hypothetically, I was given thousands of these datasets in Wooldridge, right? What would the property of all those estimates for in terms of what is their average, what is the variance, what is the distribution? So maybe from practical point of view, it's not feasible. So okay, do I have thousands of these samples? Of course you don't. You may have only one, right? But from mathematical perspective, with some assumptions, I can tell something about these numbers. So we already covered the first two assumptions. We need two more assumptions. So assumption number 3 and assumption number 4. What is assumption number 3? It says that we need sampling variation in explanatory variable. So basically it says that the variance of x should not be equal to 0. Your x variable must be variable, it must change itself, right? So, and why does that matter? This is the variance should not be equal to 0, and we know that the variance is always positive, or i.e. the variance of x must be positive, right? And instead of writing it like this, the textbook wrote it like this. So this is the same, because if I divide this thing by n minus 1, I get the variance, right? But so just these are the same, they are telling the same stories. The textbook says that the summation of xi minus x bar to the power of 2 should be greater than 0. This basically means that you should have some variability in your explanatory variable. Okay, so what if I don't have that variability? So let me show you give you an exaggerated example. So let's say this is my wage, and for education, let's make a very exaggerated example. Let's say all the observations in your data sets, they all are bachelor degrees. So all of them has only 16 years of education. So 16 years of education, thousands of these people with different wages, but their education is exactly the same. So if I tell you that, okay, this is your data set. So this is my data set, right? Now if I use OLS, so here's a very good exercise for you. If I use OLS, which one is the right answer? Line number 1, line number 2, line number 3. For all of them, the ordinary least square is going to be the same, right? So because the distances from all these dots from this line is going to be the same for all lines 1, 2, 3. So which one is the answer? So OLS is unable to pin down your slope or an intercept. So when it comes to the variance of your beta hats, it's going to kind of explode. It's going to increase. Does this make sense? And if the variance of beta hat is large, it's a very bad news, because remember, what does variance of beta hat mean? You want to say something about the relationship between education and wage. If I use model number 1, it says that there is no relationship, 0. If I use model number 2, it says, okay, there's a positive relationship between education and wage. If I use model number 3, it says, no, 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 it's a negative relationship between education and wage. So we need to make sure that this variance is not equal to 0. So we need to have some variation. It must be greater than 0. We need to have some variation in x, and with that, it's going to be a lot more clear for OLS to decide which is the best pick. So for instance, if I say in the same data set, I didn't only have this level of education, I had this level of education as well, let's say 20 years. And you know what? It seems that the observations are here. Now, looking at these two clouds of blue dots, which one is the right model? Which one is the one that the OLS is going to pick up? There you go, model number 2. There's no confusion now. So this assumption is important because of what we just covered. Assumption number 4, this is our old friend. We have seen this before. This is our 0 conditional mean assumption. This is our mean independent assumption. We are going to need that, and we talked about it in the previous previous class, that on average, the expected value of unobserved value given x must be equal to 0, because otherwise, it's not going to be a causal interpretation. So I need to have this assumption, right? So the errors has an expected value of 0 given any value of explanatory variable. So in English, we say the value of explanatory variable must contain no information about the mean of unobserved factors. I think we talked about this one in very detail in our last class. So if there's any kind of confusion, make sure you rewatch that video. All right. Now, let's summarize our assumptions. So we showed simple linear regression, assumption number 1. So what was it? Linearity in parameter, linear in beta. SLR2, random sampling. SLR3, the variance of x must be greater than 0. SLR4, expected value, 0 mean, conditional mean independence, right? So, or mean independence. U given x is equal to 0. So using these 4 assumptions mathematically, okay, the proof is beyond the scope of the class, but mathematically we can show that our estimator is going to be unbiased. So what does that mean? So we can, having these 4 assumptions, I can say at the end of the day, you were interested in the expected value of beta hat 0 and beta hat 1, weren't you, right? I can claim that if you guarantee that these 4 assumptions hold, or if you simply assume that these assumptions hold, you can say on average the expected value of beta hat 1 is going to be equal to beta 1. And expected value of beta hat 0 is going to be equal to beta 0. What does this mean? It means that on average, your estimator, OLS, is hitting right at the target. So on average, this is my population regression function. And if I do repeated sampling thousands of times, right? On average, if I take average from all these things, on average, I'm hitting right on the target. And the fun part is that this target is unobservable. I hope that you're being able to connect the dots here, what we're doing, how powerful is our mathematical tools we have. So if you're proving something that we cannot observe, and but it's not surprising because we made lots of assumptions. So what I want you to take away is that what are these assumptions? Why do we need those assumptions? And with the first 4 assumptions, what can you tell about the unbiasedness of your estimator? So this is having these 4 assumptions. We say our OLS is unbiased. Unbiased estimator means that on average you're hitting at the right slope, on average you're hitting at the right intercept. Okay, so interpretation of unbiasedness, this is very important. It's going to show up on your homework, exam, and etc. This is really important because this is a main takeaway from the first 4 assumptions. The estimated coefficients, beta hat 0, beta hat 1, may be smaller or larger. You never know. It may be smaller or larger than the population parameter, depending on the sample that it is the result of a random draw. Okay, so you never know if your slope is greater or smaller than the true slope out there in the universe. However, on average, they will be equal to that value which is unobservable. So on average, they're hitting right at a target. On average means if sampling was repeated, i.e. if drawing the random samples and doing the estimations was repeated many, many, many times. Okay, and then finally, in a given sample, this is real life, real world. When you're working on your final project, I'll give you one data set and simply one data set. So in a given sample, in one sample, estimates may differ considerably from true values. What are true values? Beta 0, beta 1. Again, what are true values in simple English? What's the relationship between education and wage? That's the true value that you're looking for. What is that coefficient? We can, and this cannot get more interesting than this, we can never know for sure whether this is the case. Okay, I know some of you guys may be disappointed at this point. What are we doing then? So this is kind of art. It's not science like 2 + 2 is equal to 4. At the end of the day, we do our best. We leverage the data, we do our best, make some assumption, and we say that, you know what, based on these assumptions, it seems that with some probability, there's a causal relationship between education and wage. That's it, nothing more. All right, now let's talk about the fifth assumption. So fifth assumption, so far we talked about the 4 assumptions. We were able to say something about the expected value of beta hat 1 and beta hat 0. So this is clear. Now we want to say something about the variance of beta hat 1 and beta hat 0. Okay, so and I already talked why we do care about the variance of beta hat 1, because we want to see this variance to be as small as possible. We are very close to that population regression function, right? So for that, we need to make another assumption. That's assumption number 5, and it's called homoscedasticity. So in order to define homoscedasticity, let's first see what is heteroskedasticity. So heteroskedasticity, you know, if it is hard for you to pronounce it, just give it a try. Heteroskedasticity, heteroskedasticity, heteroskedasticity. It means unequal variances. So what does unequal variances means? Look at that. We're talking about conditional variance here. This is y, this is x. And if your data looks like panel A, you see the variance is small at the beginning, and then the variance is going to, so if this is some measure of variance, you see the variance is getting larger and larger. So as x increase, the variance of y also increase. Does that make sense? So here, as x increase, the variance of y decrease. Here, the variance first decrease and then increase. So we call it heteroskedasticity, unequal variances. So what is the example for panel A? Income versus consumption. So if this is your, let's say X is your income, Y is your consumption, do you agree that as the level of income increase, the variance for consumption increase? Yes, right? So let's look at the minimum wage earner. They don't have the option to have a very volatile consumption. But let's look at a bunch of billionaires. Some of them are super Scrooge, some of them are very, very generous and they spend a lot. So the variance get larger. So this is example for panel A. For panel B, learning by doing. The more you practice, the more accurate you get. So your variance is going to decrease, right? So learning by doing is an example, practice versus mistake. So here, let's say X is your practice, and Y is the number of mistakes maybe. The more you practice, maybe the variance of your mistakes is going to decrease. And then another example is sometimes it's because of better data collection methods. So the example is GDP pre and post-war. So pre-war, if you look at the GDP, actually let me erase these ones. And let's say X is time, this is GDP, and this is a World War period. Before the World War, the data collection was not accurate, so it was super widespread. And then after World War, they changed the collection method, so it's more accurate. So sometimes it's a data issue. It's not necessarily a relationship between variables, right? So that was example for panel B, and for panel C, we have outliers at both ends, right? So let's say, the variance initially decrease and then increase. So we can have outliers from both ends. And I don't know, so you can think of some examples that you have in mind, but actually I will leave it as an exercise. Think about the two variables x and y that you believe that their variance is going to behave like this. Initially, for the smaller values of x, the variance is large, and then as x increase, the variance decrease, and then again, as x increase, the variance is going to increase. All right. So we know what is heteroskedasticity. Homoscedasticity, the sticity is the opposite. It says that the variance is constant for different levels of x. See, the variance doesn't increase or decrease. So this is called homoscedasticity. Now that I know what is homoscedasticity, let's talk about assumption number 5. Assumption number 5, homoscedasticity. It says that the variance of your unobserved variable, the conditional variance of unobserved variable given x, is constant. And that constant, it can be any number, so constant. And we call it sigma square. Okay, so what does that mean? Actually, I guess we have a slide in the next one that I'll look at a practical example of variance of u given x. So, but basically this means that the value of explanatory variable x must contain no information about the variability of unobserved factors. Be careful, it doesn't say it must not contain anything about the average of the unobserved factor or the unobserved factors themselves. It says it must contain no information about the variability of unobserved factors, right? Now let's look at the graphical representation of homoscedasticity. Let's say this is our y, this is our x, and guys, this is y given x means that conditional value of y given x. So for instance, if I look at what are different, imagine this is my y. What are different values of y given x? So let's say there's a distribution. So just basically these are my y versus x. I can plot the distribution. Y versus x, plot the distribution. And it seems that the distribution is homoscedastic, right? The variance of y given x is constant. So this implies that the variance of u given x is also a constant. What is the example of heteroskedasticity? Our friend wage versus education. So let's say education 8, 12, 16. Do you agree that actually you're used to see it this way? Wage versus education. Maybe you can relate to this one better. Let's say 8, 12, 16. So 8 years of education, maybe most of them are minimum earners, so the wage is going to maybe between this little number and that number, maybe between $10 per hour and maybe $12 per hour. If the education is higher, maybe the variance is going to be higher, maybe from $11 to, let's say, 15. And for master degrees, oh, sorry, this is high school diploma. This is, maybe some elementary school and things like that. And then this is bachelor. So for bachelor, maybe the variance is even higher. I think you should be able to relate to this example pretty much easily. So if I want to plot the distribution, it's going to be way more widespread. Sorry. And when it is 16 versus 12, when it's 8. So this is basically what we're seeing here, right? So the variance is smaller, then gets bigger, then it gets bigger. So this is an example of heteroskedasticity. So our wage versus education is going to be heteroskedastic, so we have to do something about it. Okay. Actually, with this assumption number 5, I'm going to talk about it why. In next class, we're going to see why we need assumption number 5. So assumption number 5, SLR5, was homoscedasticity. And then with that, plus assumption number, from the assumption SLR number 1 through 4, these 5 assumptions, then I can say something about the variance of beta hat j, or beta hat, let's say in this example only beta hat 1. So we're going to talk about it in our next class. Okay, so let me pause the video, and we're going to conclude this class with saying something about nonlinearities. How can I incorporate nonlinearities in my simple regression model? All right, so let's pause here.